Hi, this is Fiona French, and today I'll be discussing Lab 2, Lines of Charge. So for our table of contents, we'll start with an introduction and then move into fundamental concepts like the application of Coulomb's law, Newton's second law, and the superposition of electric fields, then move into the experimental setup, then computational model, then results, and then move into our discussion questions. So the main objective of this investigation was to develop a refined computational model to determine the excess amount of charge, which is Q, that is present on the tape during the interactions, and the model basically applies superposition, which divided the tape into multiple sections as point charges and then summing them for a more accurate calculation. And so for our results preview, the magnitude of this charge on the tape was 3.269 times 10 to negative 8 coulombs. And then we also saw that the lines of charge model and the point charge model were completely different based on the level of precision they were measuring. So some fundamental principles to know is Coulomb's law, which basically describes the electrostatic force of attraction or repulsion between point charges, and the magnitude is proportional to the product of charged particles, and the magnitude is inversely proportional to the square of the distance between these particle centers. And you can see the equation to the right where it is the force equals Coulomb's constant times the point charges over r squared, and then Newton's second law is acceleration is dependent on the mass of object and the net force acting on the system, but in this investigation, gravity and electric force acting on the tape should be equal and opposite. And you can also see the equations to the right. Force equals mass times acceleration. What makes this investigation different from the first lab was basically superposition, which is the vector sum of the electric field coming from various independent point charges acting on the system. And this is utilized to calculate the total charge, and you add all of them together. And you can see the E rod equation to the right, and then the gravitational force, which will be used, which is also equal to electric force. And some assumptions that you should know for this lab is we're assuming that the U-tape has around the same amount of charge and is equally distributed. The experimental setup is identical to lab 1, and the data comparisons and initial conditions are taken from that video. So basically the system is tape B, its surroundings are tape A and everything else. For the procedure, we created two pieces of equal length U-tape, and we had to make sure it didn't interact with its surroundings. Then we placed B on top of two objects and measured the distance that A had to be from tape B to make it float and repel, and then we record this distance. Some notes to be made is that the tape is known to be positive charge because it repelled from a plastic pen, which we know is negatively charged. You can see the quantitative data is on the left, which is for the tape, which is the mass, length, and width, and the distance between the two tapes. So I'm not going to go over that because I've already went over it in the first video. However, to find the gravitational force, we multiplied mass times gravity, and we got 1.964 times 10 to the third newtons. And we know because F net is 0, they will be equal to electric force, so they're the same. And then we use the E-rod equation to calculate the value of Q, and we found that to be 3.296 times 10 to negative 8 coulombs. So for a computational model, you can see to the left, it's basically the constants and initial conditions, and we have our Q, which is calculated on the previous slide. Then the photo on the right basically shows how to calculate the electric field, and then the main part of this experiment, which was the lines of charge. This piece of code basically shows all the forces and fields that were calculated and superposition when they're all added together, and the very bottom shows how the model to the right was created in GlowScript. We can see that the magnitude of the electric force is 9.617 times 10 to the negative fourth, and the gravitational force is 1.962 times 10 to the negative third, and these are not the same values. And then in the diagram, you can see that the arrow pointing down is gravitational force, the electric force is pointing up, and then tape A and B are represented by the blue and red lines, and then the electric field with all the arrows pointing up shows that. So what were the results of this experiment? We found that Q computationally was 3.269 times 10 to the negative 8 coulombs. We already went over the electric force and gravitational force on the last slide, and some assumptions. Was air resistance negligible? No, it actually doesn't apply in this situation because it is static when the tapes are floating, and then we did not treat the tape like a point charge with the charge concentrated at the center because we made it equally distributed throughout the tape. However, we did assume that the U-tape had the same amount of charge and it was evenly distributed along the length. So for some sources of uncertainty, we may have had some unwanted contact, which basically would cause the charge to be lost unintentionally when the U-tape was being handled, leading to a movement in the charge. And then the assumptions may have also led to some disparities between actual data and the computation model, so the U-tapes had differing amounts of charge, and it may have not actually been equally distributed, and data collection, there may have been possible inaccuracies in measuring the distance between the two U-tapes. So what if we had modeled each of our tapes as a single point charge like in the previous lab? So for lab 1, our point charge was 2.496 times 10 to the negative 8 coulombs, and for this one it was 3.269 times 10 to the negative 8 coulombs. And there's the big disparity due to the precision factor, and the point charge is more inaccurate, whereas the line charge is more accurate. We can see that the magnitude of the electric force and gravitational force from both these experiments were closer for the line charge due to taking account for the x and y direction. into the computational model rather than just the x like in lab 1. And lastly, why do these estimates differ and which value is more likely to be closer to the real value? So these differ due to the models being completely different, and we know that the line charge is more close to the real value due to superposition. It's more accurate because in real life conditions, the U tape was split into smaller sections and summed together as opposed to just generalizing the charges located at the center of the tape like we did in the point charge.